coming. First of all, I'm really sorry. It's one of those days that all the things that can go wrong are going wrong. So sorry for all the change. Now you've seen a new room of Workday, which is nicer to get out. So thank you so much for coming and for your patience. Just real quick, well, first of all, again, thanks for coming. This is the GD Dublin team. You've seen the three of us just running around the place. I'm Herlene. I work here at Workday. Been here for about a year and a half. I'm part of the GD Dublin for 2-3 years now. And we run events every 2-3 months. Some of them in person, some of them online. So thank you so much for coming today. You've seen the agenda anyway. We're gonna swap it a little bit, and we're gonna go first with Muhayyo and then with Toma. So yeah, thank you also Worthy for having us and giving us pizza and drinks. And Worthy is hiring a lot. We're moving to a new office at the end of the year. By Trinity, I don't know if you've seen it, but it fits 3,000 people. So they'll be hiring a lot, I'd say, in the next few months and early in the next year. So, if there's anything you're interested, let me know. If you want a referral, me or Irina, who's helped you as well, she's been so nice to help us out today. But yeah. I'm also part of the Kodu, maybe a lot of people know, of the Kodu web meetup. We've been doing them every 2 months or so. They're a bit more generic. We do socials sometimes as well. So if you don't know, it's a great place to meet people. If you like to write, we have a platform to write articles. And yeah, we are gonna first start with Muhayyo. She was here Workday. And she volunteered to speak to you about the text to 3D mesh, the journey to training. So, round of applause.
Cool. Thank you for joining, and hello everyone. I'm Muhayyo. I worked at Workday as a software engineer for 4 years, and today I'm going to talk with you. We will be going to a journey of training from text to 3D mesh, and I hope you will be with me till the end so that we will be rewarded with a demo. So what we're going to cover today, we will be talking about the problem. Not like a problem space, but like how the idea came, and then what are the problems, what are the challenges you will be getting once you want to train train a model with your use case. And then we'll talk about defining the right path. What is fine tuning? I think maybe people know what is fine tuning, but we'll be just going through the basics, and then how you go with data preparation from scratch. And we will talk about how you choose a model and how you choose the hardware that you will be running on. Then we'll talk about training parameters. We also will see where you will watch the training going forward. And then we will see the demo. And that's it. Like, what is the future improvements we can do? So you can generate images and videos from text, but how about the 3D objects? That's the first idea that came to mind. And if we think about every modality, and by modality here I mean images or videos or text, they are at high level are numbers for a LLM model, large language model, or like specifically transformer models. And for example, if we take a text-to-text generation, the raw input to model is just a natural language, which is then converted to tokens by using some tokenization for that specific model. And then you directly feed it to the transformer, and then this is how you train, and this is how your model learns. Another thing, image is also almost the same, again, in the high level. Instead of like your raw input is going to be pixels, because this is how images are represented. I think this is one of the examples. They do a compression so that you don't have a huge number of pixels. So you kind of minimize the quality of your picture, and then you fit in, and there are models that use a diffusion that removes the noise, and then you decode, you expand back, decompress. Again, like what I want to say is, the input to the model is a number. So the next one is a video. Video is also pixels, but in frames over time. So it uses similar, one of the example models, they use a similar like a compression and a diffusion and again back decompression. And again, you train your model, and model only understands the numbers. And for all these three use cases, you can think of like an input is at the end of the day a number. So what about the 3D objects? And like the examples that I gave, image, video, or text-to-text generations are mainstream, but text-to-3D is not. So if you want to decide, like, I want to train 3D objects, I want to train my model with 3D objects, and you will be having like problems of how to find the data, because it's not enough as like images. There are now billions of 3D objects out there. It's expensive to produce because you need to use some 3D software to create the 3D object. Like I think there's Maya or Blender. And then hard to evaluate means here once you train your model, there's no established evaluation evaluation metrics that you can do to learn how good your model is learning. The next is like finding the right path. So before we need to go into like the basics to understand what 3D represents. So 3D is nothing than a point in the space, in the X and Y, Z, that connects to another point with edges. And that basically represents the 3D object. So, and that's like basically the points in the points that connects to different another points. And 3D object formats, those information are formatted in different formats. You can find they're all the same. You can convert between them, but this is like a common object format. And when you're finding the right path, you need to look for if someone also did something similar, or someone also thinking about how to train a model with 3D data. And apparently at the time, in 2024 November, they published a paper that is called Llama Mesh, Unifying 3D Mesh Generation with Language Model. So in this paper, they decided to use like an OBG format. As here I showed, OBG format is one of the formats that you can represent the 3D data. And if we open up OBG format, we can see it's just vertices, like points in X, Y, Z, followed by faces, which represent the connections. For example, this is the example for a cube. And the idea in that paper was that we don't need to have separate, like a special model with different tokenization or architectural changes to that of normal text, like a language model. So the idea was just to use a language model and treat this input as a text, because these are numbers, but that numbers can be also represented as a token using the normal, like a tokenization of the large language model. So then we will have, for the 3D mesh, we will also have, again, the 3D mesh modality will be the number input to the LLM. You will use the same tokenization, and you will feed in your model with that data. So in that paper, again, they choose to fine-tune. So you can do different, there are a lot of different options to how to train the model. One of them is fine-tuning. You can also select like a full fine-tuning or partial, which is called LoRa. Like there are other ways as well. But the way why you choose a full fine-tuning, like before that, we can, I will just mention what is fine-tuning. Fine-tuning is technique to train the already pre-trained model, already model that is pre-trained with billions of data, text data, with your own focused data set. And you don't start from zero. And we also don't want to forget how to talk, because we want the input to be text, to say, please generate me, I don't know, the chair, and the output should be the 3D object. So the full fine-tuning, the difference between full fine-tuning and a partial fine-tuning is, in full fine-tuning, you're going to train all the parameters of the model. For example, your model is 8 billion parameters. It means you will be changing those 8 billion parameter weights, comparing to like a partial. And for the 3D use case, it's important because it's not enough only to train partial parameters, because in 3D, like 3D data, this kind of structure, your pre-trained model haven't seen this in the pre-trained stage. You can test it out, like asking like an already trained model to generate something in the OBG format, to say like generate me vertices followed faces. It can generate a really basic model that it maybe saw somewhere when it was trained. It can generate, for example, correctly generate the chair with 4 legs and a flat sitting, but it will be very basic, not complex. So that's why it's better to use full fine-tuning to be able to learn efficiently. The next is, once you understand your path, so you're going to go with fine-tuning. For fine-tuning, you need the data. So you want to prepare your data. I focused only on furniture. In that paper, they don't focus on specific use case. That's why, like, they have more data than me in my case, and also their mesh limit. Mesh limit means how many vertices and faces you want to have. If you have less, means you have less quality of your data, like of the object. If you have more, it means you have a good quality. And unfortunately, or fortunately, furnitures, they are geometrically complex. They will have a lot of vertices and faces to represent those curves or to represent those designs in the furniture. I sourced the dataset from open source. You can find out, like, I use Observerse, Amazon Berkeley Objects, and Alibaba datasets, and they have GLB formatted filed, and I converted them to OBG format. You can, like, yeah. So then once you convert it, you can see that this is only one point in the space. And you can see the numbers are pretty big. It's a floating point, it has a lot of data, which basically is about precision or quality of your data in the space. And if we, like, you can, before even training, you can just pre-tokenize your data to see how much token you will use for this training. You can see that for this one point in the space, you are using almost like 13 tokens. And for example, if you have one object with 500 vertices, you're already using 6,500 tokens just for vertices, not even like faces. And 500 vertices is very basic object in furniture use case. It will be like really simple, really simple object. So what you can do is you can scale down those numbers. So in some range. So in this example, I show you the range of from 0 to 128, but I tried with 0.64, 0.32 to see visually myself, like, will it break the visually the object? Is it what is the optimal solution? So optimal solution was around like 0.128, and this is the number that you're gonna get. And as you can see, with this approach, you can decrease your token size, and this is very crucial for your training. You want to have less tokens as you can. So the next thing is when you are preparing your data, you're gonna look for So every model has a limit on the context. Context length limit means how much tokens you're gonna fit in one go to the model. So you wanna understand how much that is on your data set. So as I said, you can pre-tokenize your data set to see the shape and have some statistics. For example, when I tokenized with Llama, my data set, the biggest object that I had, like that had a lot of vertices, had around 64,000 tokens, and minimum was 150, and then average was around 20,000. And I did the same data set with Gemma 3. It was twice the size of Llama for the same example, almost, and then minimum was 188, and then average is 34,000. And this will give you an idea of, like, when you're looking for a model, you want to have enough context length so that you can train your examples. You don't want to have, you don't want to you cannot break your example because it will just, your model will not learn. Another thing is when you are preparing a data, because of this context length, I needed to decrease my, I needed to only take some portion of my data. I cannot take, I cannot have this much token length even in Llama. So what you can think of, you always need to think about how you can, one of the approaches you can think of is augmenting. One of these things you can do is augmenting with rotation, specifically with 3D use case. You can take one example and you can represent it in different angles. So from one example, you have now 4 examples. So it will increase your dataset 4x, which is very good. So yeah, that's for data preparation. And the next thing is, so you know now that you have the data set, you know what is the highest context length you have in your data set. Now you need to look for the model. So you can look, so you will start your the research to see what are the layers or configuration. Is it the multimodal? Does it have vision parameters? You can find them in Hugging Face or on their official model pages. They will show you all the requirements, how much memory you need to load this model to the memory. And as I said, context length was critical for me. So if I have a longer mesh, I need more tokens. So I need a more bigger window. And I chose the Llama 3.1 and Gemma 3 because they have 128,000 context window, which is kind of enough for my use case. This is one like a small script that you can just quickly run to see the shape of the model. It will show you what kind of layers it has, how many, what kind what portion of its parameters are used for vision if it is multimodal, and it also shows you attention head, hidden attention layers. And I just want to conceptually explain, attention by itself is a huge topic that should have its own session, and there are a lot of explanation on the internet. There are a lot of visualization how attention works in transformers. So one of the ways to example here, just so that we have idea, if you have your data, which has a context limit, context window, and one torch here, let's say it's attention head. It will see, one torch can see all the input, but it can only focus on some part or some aspect of your input. And if you have more attention head, it means you have more, you understand the input richer because you have, each head can focus on different aspects. And if I give example, let's say this is the input text to the model. And I have, for example, a Llama has 32 heads. And if I have this text, and let's say it's also a big text, head 1 will say, okay, I will focus on grammar relationships. Head 7 will say, okay, I will just keep the long-range references, how the paragraph 1 will refer to the paragraph 31. Another head will look for the punctuation. Another head will look for topic consistency. and then some surprising tokens. So if you have more head, that means you understand your the data more, like you will have rich understanding of the data because you know different, how you say, different aspects of the data you're training. The model will understand. So yeah, so once you have your models selected, you are going to look for the hardware. And there are a lot of hardware providers online that give you on-demand per hour usage. Like you can just you pay only for the usage. So I use Verda. It's a European-based company, and they I think they also run on sustainable energy, which is good. Their data centers are located in Iceland, in Finland, and they are also GDPR compliant. I'm not advertising, I don't know anyone from this company, but they were very easy to run. It's straightforward, you just get what you want, and that's very important. And there are other companies, like US-based companies, that you can also search, have for, and they will have all the latest NVIDIA GPUs that you need. So once you have your hardware, and I think I chose, I didn't know what to choose, so you kind of need to try different ones to, you will just need to have to look for the memory. You need to have enough memory to run your model. So you're gonna try different ones, and then if you're getting out of memory, then you maybe want to switch to another hardware. So you have your hardware, you have your data set, now you want to start the training. And these are the training parameters that are the things that you can change, tweak, play around. On the left I have here Llama. And for Llama I chose maximum sequence length, stands for the context limit length. And I chose 20,000 because, as you saw, Llama tokenization had used much less tokens than in Gemma. That's why in Gemma I have context length of 30 for the same amount of data I have. And another thing is the batch size. Batch size means I didn't have any choice than going more than one. I only had choice one. Batch size means how many examples you can put into the first or into the input. You have one example. Can you add another example in parallelly? I couldn't because my examples are on the limit. But if you have that kind of use case, you can use this gradient accumulation, which is a very nice concept. It will help you to mimic the same behavior. You will say, I don't want to update my weights. I want to run 4 times and then update my weights. So it means I want to give, let's say, in my case, 4 examples. I want to see 4 examples and then update my weights. This is a good thing to do because if you don't have a choice to increase your batch size because of the GPU limits as well, like memory limits. Another thing is the learning rate. Learning rate is also, I have read in one of the blog posts, they say that if you want to change something or if you want to play around, this is the first thing that you want to play around. Learning rate means how fast I'm learning, how fast model updating its weights. It will just warm up and then it will go to your rate. And if you have, there are 2 different, as far as I know, learning ways, which is called linear or cosine. Linear will just warm up and reach your learning rate and then will stay in that learning rate, but cosine will just warm up and then it will go down. So it's very important. You will really see difference how your model will train because it's important to not to drastically change the weight because, especially in the beginning, because your model have never seen the data that you're training on, so you don't want to update it really drastically. Number of epochs here means how many times you want to iterate over your whole database. So 5 means here I want to model see my data 5 times. I did 10 for Gemma because I used the smaller Gemma model comparing to Llama. Llama was 8 billion, Gemma was 4 billion, because the next biggest one, 12, and I couldn't fit that in the memory. So that's why I ended up, I think, having like more epochs. But it's not like it's you will have a danger of overfitting. Like model will just remember the data. And here, create eval dataset. I did it as false, but I don't think that in the production they ever do it. Like they always evaluate their training. So evaluate training means here, in the process of training, the training will stop for a moment, and it will do inference with the data that it had never seen. That means you need to give up some portion of your data to evaluation. And that's the reason I didn't have enough data, and I also didn't have enough GPU hours, so that's why okay, I don't want to have that. But it's very good because it will, you are in the middle, you're just doing inference and seeing how it's behaving with never seen data before. I'll just here explain how that gradient accumulation of 4 means. You just only update after 4 times when you went. You don't want to update in the first step. So the training loss and eval loss is very important. If you always, rules of thumb is your training loss should be decreasing, which means your data, a model is learning the predictions that, so loss is about a single number that says how my prediction is far away from the correct answer. So it should decrease. That's a good sign. And if they are all decreasing, it's a healthy learning. If eval loss increasing, which means it's just remembering the data and it's not doing good in the unseen data. And then there is another technique that you will be setting in your fine-tuning parameters. It's called fully sharded data parallel. It's basically, you can think of how we don't want to load whole model, which is a lot of gigabytes of memory, into the one GPU. You want to shard them across so that you have evenly distributed your model weights. So this is how fully sharded data parallel helps you. It also helps you to share the gradients and optimizer states. I'm not too much familiar with optimizer states, but we talked about the gradients. So in practice, you never really know exactly how much free space you need until you run it. So you just need to start training, and you will get a lot out of memory. You then play around with your batch size, sequence length, and then maybe you can switch your hardware as well. This is an illustration of how your GPU is filled with what. For example, the weights are, for example, when the model says I have 8 billion parameters, depends on the precision, which precision you took, for example, as well. There are 14.16, 14.32. In my case, it was I picked precision of 14.16, which was kind of reasonable. And each parameter will cost you 2 bytes, which will have in total 16 gigabytes of whole model. And then you have optimizer states, gradients, and I'm not sure about actuation, I don't remember. But in total, you will get around 104. And when you apply your FSDP technique, you kind of evenly distribute. If you have 8 GPUs, you will distribute to each of them 13. And this is a smaller Gemma model. It's also just to show what goes to the memory. And you need to watch. So you start your training, and training can go I don't know, many hours, days. So you want to see what's happening, and this is a weights and biases. It's I think the commonplace people use is MLOps dashboards that shows you what's happening with your training. You log in your parameters. You say after how many steps you want to log, and this will show you the training loss, what is the epoch, and what's happening with the learning rate. And it's important because you need to see what's happening so that maybe you can stop your training early on without losing a lot of compute. So now I will show the demo. So I put here a little demo, and I only show Llamas 3.1. It's not connected to any GPU. It's just a pre-generated object. So, so let's say like I want to create a 3D model of a sofa. It's just an animation. This is one of the generations. If I do twice, I should say another one, yeah. And this is whole like generated by LLM. I don't know why it's not showing correctly. This is a cabinet. I added these materials. They are just, I don't know, I just picked up materials. They may not be fitting the use case. It will apply to all the all the faces here. We have chair. Yeah, I don't know why it doesn't have legs, but at least it has a good structure. Do I have another? Yeah. Then the table. Yeah, I just also want to show that it's not very great, but I do think that I didn't have enough data. So yeah, that's the demo, and the last thing, what is next? So when I was trained, I only trained on the 3D geometry, basically, the points and the vertices. But there is a concept of a UV mapping. If you have any 3D object that is fully like with texture, they will have in the OBG the UV mapping information as well. I just didn't have enough token. I couldn't fit a lot of data. That's why I removed UV mapping. But if you have UV mapping, when you have texture, 2D texture, you can very organically or naturally apply it to your model. And another thing is, as I said, there's not much, the 3D objects are scarce, there's not much data, but I think, I don't know when they released this, maybe this in the beginning of this year or last, at the 2024 December, Meta, they open source their SAM 3D, which is segment anything. You basically give a 2D image, and then you select the object, and it generates really good, accurate 3D structure, even though it didn't see how the back looks like. You can try it out there. You can put your any data. So I picked up some images from IKEA, and it was so crystal, so good. And that means you can generate, because we have unlimited 2D images, so we can use potentially this one to generate unlimited data set with good quality and label them. So the training is model runs in the good quality data, because as you know, a garbage in, garbage out, so it's better to have and spend much time in the data preparation. That's it. Thank you. If you have any questions, you're welcome to ask.